Hi, my name is Savannah Harris, and this is my Lab 3 video presentation. For this lab, we were given a CSV file that contained the X and Y position data for a star revolving around a black hole of an unknown mass. We were given a code to edit in order to find the forces acting on the star in the parallel and perpendicular directions, as well as the total net force. The end goal of finding these forces was to use the gravitational force equation in order to solve for the mass of the black hole. This lab tested our abilities to use fundamental physics theories such as Newton's second law and the splitting up of forces between the perpendicular and parallel components. So just a quick overview of what I'm going to be doing. First I'll do a code demonstration, a code breakdown, and then calculations, showing you the calculations I did to find the net force and the mass of the black hole. So this is my code, and this is what it looks like when you run it. So as you can see, there are 3 arrows. Each of those arrows signify a different force that is acting on the star. So they're all the gravitational force, but the black arrow is in the parallel direction, blue in perpendicular, and the yellow is the total net force. This is my print screen, and I'm going to go over what all of these mean in just a minute. So going back to my code breakdown, the first thing that I edited was the mass of the star. I just inputted the mass that was given to me by WebAssign. I also put in the delta t as being 86,400 because that's the number of seconds in the average Earth day, and t was kept to be equal to 0 for our initial time. This part of the code reads in the CSV and creates a list containing the x and y positions. I made edits to this part of the code in order to calculate the x and y velocity. To do this, I made a function for the change in the position for both x and y called delta x and delta y respectively. This was found by taking the x and y position values and subtracting them from the x and y values that came right before them in the CSV file, and then dividing it by delta t. So for this part of the code, I used the observed position data to find the velocity, both initial and final, the momentum, both initial and final, dp dt, and then I calculated dp dt parallel and perpendicular. I also used this to find the fnet perpendicular and fnet parallel. This code uses path motion that we know to find the forces using Newton's second law. So here's a pretty good time to bring up the differences between fnet perpendicular, fnet parallel, and fnet, and then comparing it to dp dt perpendicular, dp dt parallel, and dp dt. So basically the difference between fnet perpendicular and dp dt perpendicular, and respectively comparing the parallel and the total of f versus dp dt. So all of them are equal to each other, meaning that fnet perpendicular is equal to dp dt perpendicular, and so forth, but they are found using different equations. So for instance, fnet can be found using trig and fnet, while dp dt is calculated by multiplying the magnitude of momentum and velocity and dividing by the radius of the kissing circle. dp dt parallel is equal to the magnitude of momentum final minus momentum initial divided by delta t, and then multiplied by p hat. And then fnet and dp dt are both found by adding their respective perpendicular and parallel components, and we know this is to be true because of Newton's second law. So basically, each is equal to each other, so fnet perpendicular is equal to dp dt perpendicular, fnet parallel is equal to dp dt parallel, and fnet and dp dt are equal to each other, but the way you calculate them is different. So for instance, if you were missing one of the variables within the fnet perpendicular equation, you could solve for dp dt perpendicular, and then once you had a value for dp dt perpendicular, you could plug it in for fnet perpendicular and then solve for the unknown variable within the fnet perpendicular equation. So this part of the code sets up basically all the visuals. The only thing I changed here was the arrow scale. I made it 1 times 10 to the negative 14th just to make it so that the arrows weren't so large that they overwhelmed the entire screen. So this is my print screen. Basically, I set up a couple of different print lines, but the most important thing that I did here was set up the gravitational force equation and isolate for the mass of the black hole, which is what we had originally intended to find. So I set the mass of the black hole equal to the magnitude of Fnet times R final squared divided by the star's mass times the gravitational constant, and I printed those out. And here you can see a bunch of different print lines. The most important is probably the mass of the black hole is equal to 1.99 times 10 to the 31st, because that is the mass of the black hole that I solved for. This lab also asked us to investigate a what-if question. That question was, if you replace the current black hole with a different black hole with a different mass, would you still be able to tell a difference by observing the motion of the star? And the answer to that is yes. Changing the mass of the black hole would change the force of gravity acting on the star, which in turn would change the position data because a different force would be acting on it, so the star would move differently. And in conclusion, just to wrap up, in this lab we used observed position and movement data to find the net force on a star through dp/dt, and then used that force to find the mass of the black hole through the gravitational force equation.